Okay, in this lecture we're going to be learning about ozone and what it is and how chlorofluorocarbon pollution has contributed to the loss of ozone in Earth's stratosphere. So in terms of some general goals and an outline, we'll answer some key questions including what is ozone and where is it located, how does it function to protect humans from harmful UV radiation, in other words, what's the mechanisms by which ozone does this, what are chlorofluorocarbons and where do they come from, how do CFCs actually deplete ozone in terms of a mechanism? Where is the ozone hole? As we'll see, this is actually a regional phenomenon, not a global one. When does it occur and how does it happen? And then lastly, what policies have been instituted that has helped to mitigate CFC or prevent CFC pollution? Okay, what is ozone? Ozone is a molecule composed of 3 atoms of oxygen, so its chemical formula is O3, and so this is its general chemical structure. You've got 3 oxygen atoms bonded by covalent bonds. Now, ozone is a gas under normal atmospheric temperatures and pressure, and it's actually a very, very tiny fraction of our total atmosphere. Only minute amounts of ozone exist. But as we'll see, small amounts don't mean that it's not important. So basically, for every one ozone molecule that exists in the atmosphere, there are about 10 million other air molecules. Now, where does it occur? Well, 90% of it occurs in the stratosphere. So here, if we look at altitude along the y-axis and ozone amount in terms of its partial pressure, what you can see is that this peak occurs basically right here in the stratosphere. So this peak here accounts for around 90% of all the ozone in the atmosphere. You see a little bit in the troposphere up high here, and you see another blip of it a little bit high here in the lower troposphere. And we'll talk about this when we talk about photochemical smog, because this isn't natural. This normally doesn't occur under natural systems, but we've actually created smog, and one of the pollutants in smog is ozone, and this is actually generally referred to as bad ozone, and ozone up in the stratosphere as good ozone. So as I mentioned, big things come in small packages, and ozone is a good example of that. Ozone is a small amount of our atmosphere, but it's vital for our human health. So why ozone is vital for our human health depends on basically what ozone does with UV radiation. So if you recall from Planck's law and the temperature of the sun, right, we know that the primary forms of electromagnetic radiation that reach Earth's atmosphere are UV to a small extent, mostly visible, and then also a good portion of infrared. So here is the entire spectrum, okay, and so what we're looking at basically is UV light is at the more energy intense spectrum. These are short wavelengths but high frequency. Then we have our visible spectrum, and then we have our infrared. And what you see is we actually have the UV spectrum is broken out into 3 other sort of subcategories, much like the visible spectrum is broken down into red, orange, yellow, green, blue, indigo, and violet. So here we have UVA, UVB, and UVC. So UVA is going to have the longer wavelengths, and UVC is going to have the shorter wavelengths. And so this also means that a single wave of UVC is actually more energetic than a single wavelength of UVA. All right, and so the key when it comes to ozone and human health is that if you look at the absorption spectrum here, so where we see here's wavelengths from infrared to UV light, and this is the percent of the incoming radiation that's actually absorbed. And if you recall, these are all of the greenhouse gases, so they all see basically absorption peaks in the infrared spectrum. But what you notice is that ozone and oxygen also absorb in the visible spectrum, but they also absorb here in the UV spectrum. So now let's talk a little bit about UVA, B, and C in terms of their general qualitative impacts on human health. Well, UVA is the least damaging. This leads to sort of premature aging of the skin by looking at wrinkling and sort of decreases skin elasticity. UVB is the more energetic one, and this causes sunburn and cancer, melanomas. And UVC could be potentially the most damaging because it's the most energetic, but as we'll see in later slides, 100% of the UVC wavelengths are absorbed in the stratosphere and don't actually make it to the surface of the Earth. Okay, so let's talk about the mechanism by which ozone protects us from this UV light. And as you might suspect, the main process here is absorption. If you recall, what happens in the absorption process is electromagnetic radiation comes in. a certain wavelength of it gets absorbed. That raises the thermal kinetic energy of a molecule, and as a consequence, that molecule will re-radiate or emit electromagnetic radiation, but at a lower wavelength. Okay, so the actual mechanism is called the Chapman process, and it's a 4-step process, and it's actually a continuous sort of loop, a synthesis and destruction of ozone. So let's take this sort of step by step. So these two figures show the 4 different steps in the Chapman process. So step number 1 basically occurs when molecular oxygen, actually O2, right, UV light comes in and strikes the oxygen molecule, right? And we get absorption. What happens when we get absorption? The molecules begin to vibrate, rotate randomly, and then also randomly just displace. So their thermal kinetic energy increases. So we get thermal kinetic energy generated in this step. And that thermal kinetic energy and the motion between the molecules is so strong that it's actually able to break the chemical bond between the two oxygen atoms. Now, a key thing is that oxygen actually absorbs the wavelengths that are less than 240 nanometers. So if we look at this diagram over here, this yellow box shows that this is what oxygen, molecular oxygen, is actually absorbing. And so it's mostly, almost exclusively in the UVC spectrum. Step 2 is these two what we call radical oxygen atoms go flying through the atmosphere and basically end up colliding with molecular oxygen, O2. And then what happens is they actually form a chemical bond and we get O3. So this is the first step where we actually form ozone in the stratosphere. This step also generates thermal kinetic energy. Step 3 is another absorption process, but instead of it being molecular oxygen that absorbs UV radiation, now it's ozone itself that absorbs that UV radiation. Now, the difference is that ozone absorbs different wavelengths. It absorbs wavelengths less than 320 meters. So what I've done is I've outlined in yellow up here what that looks like. Okay, here's 320 nanometers and it's going to absorb less than that. So what you can see is that we actually absorb a good chunk of the UV that comes into Earth, and basically the entire box of UVC is covered. And so this is why none of UVC actually makes it past the stratosphere. Okay. Now, of course, since we have an absorption process here, right, it's going to increase the thermal kinetic energy of ozone, but also that thermal kinetic energy, that vibration, is so strong that it can actually force one of the oxygens. You can sever one of the chemical bonds between one of the oxygens and the other, and that goes flying through space again. Now, what happens up happening is that free radical oxygen comes flying and comes into contact with an ozone molecule, also generates thermal kinetic energy, but in the process basically splits the ozone molecule into 2 molecular oxygen molecules, and then that means we basically start all over at step 1. So basically steps 1 through 2 are the synthesis part of the Chapman process where we create ozone, and then steps 3 and 4 are the breaking down of ozone into the 2 molecular oxygens, and then that goes right back into step 1. So basically, how does it protect us from UV radiation? Is it absorbs it. When a molecule absorbs it, we convert it to another form of energy, that's thermal kinetic energy, right? Of course, because it has temperature, it's going to emit other wavelengths of radiation, but it's different ones. It's not UV anymore. So the UV basically is used up in this process to generate other forms of energy. Okay, so in terms of human health and what gets absorbed, we see that about 99% of ultraviolet light gets absorbed by stratospheric ozone and molecular oxygen. That means that 1% under natural conditions actually reaches Earth's surface. So let's take a look at that 1%. 99% of that happens to be UVA, and 1% happens to be UVB. Okay, and I showed that diagram before of that box, right? And where the overlap of the wavelengths are that get absorbed by UV, by ozone and oxygen. And we saw that UVC is completely absorbed, and so this doesn't make it down here. The majority chunk of the blue boxes also gets absorbed, so only a little bit of UVB makes it down. But the UVA box in the previous slide is actually not completely covered, and so we see quite a bit of UVA, or mostly UVA, out of all of these reaching the surface of the Earth. Now, the other thing I want to draw your attention to is basically this absorption of UV radiation is the reason why we see the temperature profile in the stratosphere. If you recall the troposphere, right, we see warmer temperatures at the surface, colder at the top of the troposphere, because why? Because we absorb radiation at the surface of the Earth, generating a lot of thermal kinetic energy. And also, as air rises, we get adiabatic cooling, which also tends to cool up here. But we see this sort of reverse temperature profile where it gets warmer in the stratosphere, and that's because this is where we see 90% of ozone. And since ozone absorbs that very powerful UV radiation, we generate a lot of thermal kinetic energy, leading to this increase in temperature with altitude within the stratosphere. Okay, now let's take a look a little bit at CFC pollution and how this is going to reduce the ozone. So there are many different types of CFCs, and CFC stands for chlorofluorocarbons, and that's because of their chemical composition. Chloro, because they have chlorine. Here's a chlorine, 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 chlorine. Fluoro, because they have a fluorine. Here's a fluorine. Here are two fluorines. And carbon, because at the center of this molecule is a carbon atom. And the two most common or important CFCs are CFC 11 and CFC 12. Not really important, but just want to give you a sense of the two most important ones. Now, CFCs, there is no natural source of them. Okay, they were basically created in a lab by DuPont in the 1930s and went under the trade name of Freon. Now, they're completely non-toxic to humans. That's great. They're not flammable either, so they're highly stable, and they're not reactive. And so these are three great properties for using it in human products. So for example, CFCs were used in the production of styrofoam. They're also used as a refrigerant in air conditioners and refrigerators and freezers, and they're also used as a propellant in aerosol cans. All right, so you don't want necessarily flammable stuff and reactive stuff in any of these products. So they were a great invention for us, for our human needs. But as it turns out, they turned out to be harmful for the environment. And if you recall back from the scientific method chapter, we talked about that James Lovelock was the first person to detect CFCs in the atmosphere. But it wasn't until Frank Sherwood Rowland saw a presentation by Lovelock talking about this that the ball started to really get rolling and get a sense of what the environmental impact would be of CFCs. So Frank Rowland at the time, back in the early 1970s, hired a young postdoc in Mario Molina, and basically they tried to answer the question of what happens to these CFCs in the atmosphere now that we know that they're there. And so in 1974 they developed a hypothesis that basically the UV energy in the stratosphere would break up these CFCs and basically cause the depletion of ozone. All right, that's what their hypothesis was. Now, they came up with remember that hypothesis is just an explanation. A theory is going to be more mechanistic, like how does this happen? All right, and what was interesting about Rowland and Molina's research is that they actually never had to do any experimentation. Actually, they took what they knew from existing information from existing scientists, took what they know about the chemical reactions that occur in the atmosphere, and put these together to develop their model of how ozone would deplete, or sorry, CFCs would deplete ozone. So their theory has many parts. Here are some of the major components of it. The first is that they hypothesized that CFCs would accumulate in the stratosphere, largely because there would be no chemical reactions in the troposphere that would break them down. Next is that since they would accumulate in the stratosphere, they developed a step-by-step photochemical reaction that they believed would actually break down CFCs. All right, and so that mechanism is like this. We take the CFC molecule, carbon, fluorine, 3 chloride ions, and basically they're going to absorb UV radiation. All right? What this does is that increases the thermal kinetic energy of these molecules and is strong enough that that motion can sever the chemical bonds between one of the chloride ions and the larger CFC molecule. So that chloride ion goes flying. Right? That chloride ion then comes into contact and collides with an ozone molecule. Right? It basically steals an oxygen away, leaving oxygen and chloride bonded together and molecular oxygen. Okay? Then when a free atom of oxygen collides with this C and L, chloride and oxygen, chlorine monoxide, basically the two oxygens combine to form molecular oxygen, and the chloride ion is then free to go on and repeat step number 3 here and collide with another ozone molecule. Now this may not sound all that bad, but basically this leads to a chain reaction. And the residence time of a single chloride ion is 1.5 years. And in that 1.5 years, it can destroy 100,000 ozone molecules. right? And when we put more and more CFCs up there, that means there's more and more chloride ions, which means they distort even more and more ozone. All right, so the step-by-step chemical reaction was part of the theory, and the last thing was that they, based on the mechanics of this chemical reaction, what they knew about UV radiation, they basically predicted that there would be a 17 to 13% reduction in ozone concentrations in the stratosphere. All right, that's all they knew in 1974. All right, there was very little actual empirical evidence that this was going to occur, but based on scientific understanding of the system, this is what they would predict to be happening. And it took basically 10 years later by Joseph Farman and his colleagues working over in Halley Bay, Antarctica, to finally get the empirical evidence they needed to basically provide supportive evidence for Roland and Molina's theory of ozone depletion. And so Joseph Farman's group was the first group to actually detect a decline in ozone concentration. All right, so here you can see that basically they've been monitoring ozone concentrations from 1960 to about the mid-1980s or 1982 or so. And so this is in Halley Bay at 76 degrees south. Okay, and what you can see is that these sort of dark vertical lines show basically a precipitous decline in ozone from 1960 to 1980, basically over a 2-decade period. Now, not only that, but this actually shows a 50% reduction in ozone. If you recall, Roland and Molina predicted a 17 to 13% reduction in ozone. So this was much larger a magnitude than Roland and Molina had predicted. And we'll actually explain why this is actually unique to Antarctica in a little bit. So finally, they had the empirical evidence they needed. So what has been the impact of the CFC emissions and loss of ozone? So here goes the record of ozone from 1965 to 2005, and what you can see is that this is percent change. So this is 0%, no change at all, basically from 1960s to about the early 1980s or so. And then we start to see this very, very big drop in global ozone. Okay, now the other interesting, but that global ozone pattern is just an overall general pattern, and there's some sort of interesting seasonal and spatial variation that we see that contributes to that pattern that we need to understand. And so this shows a map of the southern hemisphere and the concentration of ozone, which basically orange and yellow would be high, and the blues and the violets and the reds would be very, very low. So within the southern hemisphere, and this shows from 1979 to about 2000, what you can see is that the depletion of ozone is much greater actually over Antarctica than it is anywhere else, and that depletion here gets worse and worse and worse all the way into 2000. The next thing we see is that there's seasonal variation, and so this is looking at global ozone, but instead of sort of smoothing the average out, annual average, and looking at it this way, basically we're going to add all the sort of day-to-day or month-to-month variability that we see in these ozone concentrations. And what you can notice is we see the same general trend, right? From about 1980 or so, there's this decline through the mid-1990s, and then it sort of becomes sort of constant or unchanging from there on out. But the other thing you notice is that there's a consistent cycle. An increase and then a decrease, an increase, then a decrease, an increase, then a decrease, an increase, and then a decrease. And what we'll see is that actually this low, when we see that the minimum amount of ozone consistently occurs in the springtime. So basically what we see in the previous slides is that ozone depletion is a global phenomenon, right? All over the globe, ozone has been depleted since the 1960s. This ozone hole, where there's a really substantial drop in ozone, only occurs over Antarctica and only occurs during the southern hemisphere spring. So what's so special about Antarctica? So if we want to understand the ozone, we need ozone hole. We need to understand the mechanism by which it forms. It's much more complex than the mechanism I just described about CFCs depleting and how they deplete ozone, although that's involved. And so the story starts in the wintertime. And the environmental conditions set up to cause the spring ozone hole during the winter. So what happens during the winter? Right? Basically, insolation is maximum in the northern hemisphere, and the southern hemisphere gets very little light. Now, if you're in Antarctica, there's actually no light at all for 24 hours, for entire day for long stretches for months. All right, so if there's no insulation, nothing gets absorbed, and basically it's very, very cold. This very, very cold feature of Antarctica causes what's called a polar vortex to form. And a polar vortex is nothing more than basically this sort of isolated spinning air mass. So here you can see a polar vortex actually forming over the Arctic, not Antarctica, but it sort of rotates around. All right, now what this polar vortex does is it isolates the air over Antarctica, meaning that any CFCs and ozone that happen to be present within this ozone, within this polar vortex, get pulled toward the center. So you aggregate CFCs and ozone together, almost like you're starting to cage them up. All right. Then, throughout the winter, it gets very, very cold, so cold that we end up with negative 80 degrees Celsius. And this allows actually stratospheric clouds to form. And stratospheric clouds aren't made of liquid water, but actually ice crystals, because it's so cold. So here's an ice crystal here. And in essence, what happens is the combination of CFCs, ozone, and then another molecule, HNO3, nitric acid. Basically, what ends up happening is these three combine on these ice crystals. And the HNO3, this acid, plus the CFCs is actually strong enough to basically pull off a chloride ion from the CFCs, much like UV radiation does. But unlike in UV radiation, where the chloride ion is free to sort of move around in space, the ice crystal basically binds these chloride ions, so they're not free to move around, and they're stuck on these ice crystals. Then the hole forms in the spring. Now, why does this happen? Well, we still have the vortex, so that means we still keep the air trapped in there, this sort of cage match where we combine CFCs and ozone. All right, but we start to add light. Okay, and when light happens, what do? We start to melt these ice crystals. And when that happens, basically the chloride ions that were bound to these ice crystals are free and are released, and they start flying through the atmosphere. Okay, so the insulation that comes in basically activates those chloride ions, and then we generate the whole Roland and Molina mechanism of destruction of ozone. Okay, now the hole disappears in the summer because the vortex breaks down, right? And what that happens is it allows ozone from higher latitudes to come in and replenish the ozone that's been depleted inside the polar vortex. Okay, so what policy has been instituted? Basically, Roland and Molina lobbied and advocated for stopping the emissions and productions of CFCs starting in the mid-1970s. And it wasn't until 1987 when an international agreement called the Montreal Protocol came about, where basically all the nations that came together agreed that they would reduce CFC production by 50% by 2000. Then it was amended. Things were actually going so well that we're able to meet this 50% goal that in 1990 they decided to amend that. And they said, forget about 50% reduction, we're just going to phase things out by 2000. Okay? And then give developing countries actually a little bit of a break and have them phase it out by 2010. And then things were going so well by 1992, they said, you know what, forget it, we're going to phase it out by 1996. So basically by 1996 we effectively had zero emissions of CFCs globally. All right, so here shows CFC production from 1950 or so on. Right, then we had the first ozone depletion reported in 1974. The Montreal Protocol here was signed in 1987. We had several amendments, and then by 1996 we had seen the thousands of tons of CFCs in the atmosphere in terms of emissions was much lower. Okay. Now, that doesn't mean that the concentration of ozone has dropped rapidly. So here, as we look at effective stratospheric chlorine, these chloride ions, what you see is that actually we haven't dipped down very much at all. But if you remember, these chloride ions have 150-year residence time. So even though we've cut off the emissions, the chloride ions and the CFCs that we've already put up there are still there, and it's going to take them about a couple hundred years basically to bring those levels back down to where they need to be. Now, although we're not all the way there yet, this showed a very collective and rapid response on the part of the international community, and it was actually effective. We've actually cut CFC's productions, and we will start to see the benefits of that strong policy over the next 100 years or so. Okay, so that's the story of ozone, its benefits for human health, and why CFCs have contributed to reductions in ozone.